Data QC is always a difficult task. This week, we'll look at a glitchy temperature reading and clean it up with just a few lines of Python. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. This week, I want to take a look at a way that we can clean up some glitchy data. So I've got a file here that's got two temperature sensors. We'll just look at one, but both of them have this problem of they exhibit glitchy natures. They randomly drop out. In fact, you can see in the first few lines here, we go from a reading of 17.562 to a reading of minus 0.062. So something is clearly wrong there. And this isn't uncommon. You get back from a field campaign or you download a large archive of ASOS data and there's a sensor problem or a communications problem or something happened between the real world and when those bits got to your computer. So let's open up a notebook and look at what we've got to deal with. All right, so I'm going to import NumPy. I'm going to import matplotlib. And I'm going to use my matplotlib inline magic. Given the nature of that file, I'm just going to use NumPy's load text method. So the temperature is np.loadText. I'm using the tab complete, and DS18B20 is the name of this particular sensor. I'm going to skip the header row, and I'm just going to use that first column because I'm only going to look at one sensor. After we get our data, we could look at things like, well, what's the shape? In this case, I have just over 14,000 readings, so this is quite the time series. The next thing that I would probably do, I could look at some statistics, but first I'm going to make a plot, just a quick dirty plot. I'm going to create a figure and an axis. And then I'm going to call plot on temperature. And I'm going to go ahead and future-proof myself here because I know I'm going to be trying different things. And I'm going to label it raw data. And I'm going to put a legend on. Okay, so having a look at our plot, we definitely see there's a problem. Looks like our temperature trend is up here. So we descend from 17 down to a little above 15 and then start coming back up. But we've got all of this glitchiness and there's a lot of it there. So how can we do this? Well, the first thing that you think of might be, well, I'm going to do a mean, a running mean. I'm going to take a window of 10 or 20 or 50 data points, and I'm going to take the mean of that and then move that window over and do it again. So let's try that. So the mean filter temperature, I'm going to use NumPy's convolve, and I've talked about this in past MetPy Mondays. This is just a quick, fast way to do a running mean. I'm going to take an 11-point convolution. And this is because some of the other methods that we're going to look at later require an odd number for a window size. So I'm going to go ahead and use an odd number here so things are exactly comparable. So we're going to convolve that with the ones with temperature. I'm going to say that I want a same length output. And then we have to normalize that. So we're going to divide by 11. All right, so let's make another plot. Again, none of this is anything too shocking, but now our labels are going to become more important. Use tab completion. Okay, well, it's better, but it's still not good. The spikes were just reduced. Now we could increase the window of that to try to get more good data points and get the mean closer to what our real data are. But there are so many glitches in here, and they're such a different value. If you have just small glitches, like say we had glitches of a degree or two around the true reading, this probably wouldn't be as much of an issue, but we have a glitch of 17 degrees. We're basically going from a reading to a 0. So a running mean doesn't really work so well, unfortunately. One thing that we can do in an effort to not tamper with the data any more than we have to is we could say we're going to look at a data point, and if it is more than some tolerance away from the mean of the data points around it, we're going to call it a glitch and get rid of it. So let's see how that might look. I'm going to create an array called removeIndex, and it is going to contain where the absolute value of the temperature minus the mean filtered temperature is greater than 2. So what does that mean? That means we're anywhere where the difference between the individual reading and the mean of that 11-point window that we've got is greater than 2 degrees, we're going to call that a glitch. So this would be a Boolean array, an array of trues and falses. I'm going to create a copy of my temperature array called mean removed temperature. And then in mean removed temperature, I'm going to take those true Boolean values that are in removeIndex, and I'm going to set them to be nan. So that takes anything that we think is a glitch and just sets it to nan. So now let's try making the same plot again. So we're going to plot our raw data, and then we're going to plot the mean removed temperature. And then we're going to, let's put a legend up, and then we'll set some axis limits later. Okay, so this looks promising. We've got now a thin orange line here. We're not seeing any significant glitchiness. So now let's set the Y limit to be, let's say, from 15 to 18 degrees. And we see that we have preserved all of the noise that's in the real data, but we have gotten rid of all the glitches. So this is not a bad solution, really. It accomplished the goal of despiking our data. But I still know that this is probably noise, and it's small. It's 1/4 of a degree or less, but this is probably noise, and there might be some other trends in here that I want to see other than this cooling and warming trend. So I want to show you one more filtering tool. And again, these are not necessarily things like low pass and high pass filters. They certainly have connections to that, and digital signal processing is a whole field. But this is one that we're going to steal from the world of image processing, and it's called the median filter. This is something you would often do to an image before you run an edge detector or some kind of classifier on it. It's like a running mean, but instead it's a running median. So it helps us get rid of some of those outlying data points, and really does a pretty good job, in my mind, of effectively low passing your data. Though how the window width changes the frequency content, that's a whole nother topic again. So I'm going to take a median filtered temperature, and we're going to need to do an import. So from scipy.signal, I'm going to import medfilt. We're going to run it on our raw temperature data, and we're going to use an 11-point window. If you look at the documentation, you will note this is one of those functions where you need to have an odd number of points for your window size. If you're running on very large data, I would go to the IndieImage submodule in SciPy and use median filter from there. It actually runs significantly faster if you're on a very large data set. Okay, so once again, we're going to make our plot. So temperature, we're going to label it. Our median filter. Okay, this looks even more interesting. It's a thinner line up at the top. So let's go ahead and set our limits from 15 to 18 again. Or that should be X, there we go. And now we see that it actually has pulled out a little bit of sinusoidal variation in here. If we wanted to, we could also plot the mean removed data. And we can now see that it has a slightly lower noise amplitude, if you will, say maybe the RMS amplitude. But let's look at here where we've got this rapidly descending temperature. We can see that it is indeed removing a lot of that, what's probably noise. And here we're picking up on some other sort of variation. So this is a few simple ways that you can despike your data or do some basic filtering of your data. And it really helps when you're QCing or trying to get a quick look at things, or even if you want to go ahead and make some plots that are a little bit more cleaned up. I hope that you found this useful, and I'll see you on next week's MetPy Monday.